Okay, now I think we're ready. So. It's just yesterday. Feels like longer ago, but it's not. So I'm just gonna do a little bit of review. Today we're gonna do hypothesis testing for two sample proportions. Of course, there's some more terminology, which I know you guys love. Things to keep track of. Let's start with a smidge of review here, because it was just yesterday. Oh, so funny. This morning, I went to close the door, and as I'm walking to the door, I said, oh, I better close the door so I'm not yelling at Steve all day. And then, but Steve was also closing his door because I was being so loud. So he poked his head in. He's like, are you talking about me? I'm like, yes, I'm talking about you. So what we landed on yesterday was that we can use a confidence interval to informally test the hypothesis. We can use a confidence interval to informally test the hypothesis. What we didn't say yesterday was what that hypothesis was. We just kind of got there organically by saying, okay, if I'm hypothesizing about the difference in proportions, and my initial hypothesis, my null hypothesis, is going to be that they're the same, well, then the difference would be 0, right? And so today we're going to formalize that, and we're going to say that, okay, well, what we're testing is technically the null hypothesis that P1 minus P2 equals 0. What's really, really nice is that this will always be your null hypothesis for two sample proportions. So if you read a question and you decide, okay, this is a two sample proportion question, then this is your null hypothesis. Or just to give you an alternative, and I shouldn't say alternative because alternative hypothesis, but just to give you another option, if P1 minus P2 equals 0, you could write this as P1 is equal to P2, which I prefer, just because I find that it makes it look a little bit cleaner. It's a little bit quicker to grasp, right? But we are hypothesizing about the difference in the two population proportions. So technically, this is the hypothesis that we're testing. But what's really, really nice, like I said, is this will always be the null hypothesis for two sample proportions. This will always be the null hypothesis for two sample proportions. Right. So we're going to need to read the question, decide what type of question it is, but then once I know it's a two sample proportion question, it doesn't matter how you like to write it, right? It's going to be one of these, and it's going to be one of these always. Yeah. So then what we did with that number line that we drew, right? We said, okay, I can draw my confidence interval on the number line. And if 0 is in the interval, right? So if this null hypothesized value is in the interval, then we do not have enough evidence to reject H naught, because I'm 95% confident that 0 is one of the options. Yeah. So once we have a confidence interval, okay, we check to see if, and I'm going to talk about it generically because we can do this for any hypothesis, any type of question, right? And so I'm going to talk about the null hypothesized value, which is 0 in this case. Okay, so once we have a confidence interval, we check to see if the null value or the null hypothesized value, right, P naught or 0, right? Those are the only ones that we've seen so far. We're going to add to that list, right? But just so you get an idea, is contained in the interval. If it is, right, if the null value is in the interval, null value is in the interval, then you do not have enough evidence to reject H naught. Do not have enough evidence to reject H naught. If the null value is not in the interval, we do have enough evidence to reject H naught. And if I'm rejecting it, I should probably say in favor of what? In favor of HA. Yes.
You used the term informal test, but then we seem to be pretty confident in acting.
Yes. It's only because we're not using the p-value approach. So the p-value approach is still considered the formal way to test a hypothesis. But the field is sort of moving towards confidence intervals instead of p-values, but we're still stuck on p-values as the formal way. So we can use confidence intervals. The problem, or not the problem, but the thing with confidence intervals is you can only do a two-sided test, right? Because you're always going out and you're finding the central 95 or 90%, right? So it's only doing a two-sided test. Whereas if you really, really, really want to do a one-sided test, you'd have to do some tweaks, but then you would just use the p-value approach. So that's why I say informally, but then with a very formal conclusion. All right, so that's kind of where we ended up yesterday. Today we're going to talk about, all right, what's the formal hypothesis test for two sample proportions? Of course, we have to introduce a couple of new things, okay? And then we'll start an example. I suspect we won't get through it all, but we're going to try. So a formal hypothesis test for two sample proportions. So where we're going to start is with the null hypothesis, which we already outlined, right? And so our null hypothesis, I'll start with the one that I prefer to look at. P1 is equal to P2, or on the other side here, these are equivalent, right? P1 minus P2 is equal to 0. So as long as you're able to use these interchangeably, it's okay if you have a favorite, that's fine. But just recognize that these are the same, right? And the second one, so the one that I don't love as much because there's more symbols and things, right, to keep track of, is what we're technically hypothesizing about. We're hypothesizing about the difference in population proportions, right? So it's more proper. Our alternative hypothesis, again, we have three options. P1 is not equal to P2. In terms of the difference, right? The difference, if they're not equal to each other, is just going to be not equal to 0. So that's fine, right? P1 minus P2 is not equal to 0. That's what we call a two-sided test, right? When I don't care which direction it went in, I just want to know, is there a difference, right? So we call this a two-sided test. Whereas if I'm concerned with one extreme, right, is P1 less than P2? That's an option. P1 is less than P2. How do I translate that into a relationship with 0? Takes a little bit of thinking, not too bad, right? If P1 is less than 2, then P1 minus P2 must be less than 0, right? Or you can subtract P2 over to the other side. However you want to get there is fine by me. The other option is P1 is greater than P2, which would mean that if P1 is greater than P2, then you're subtracting a larger or a smaller number from a larger number, which means it's going to be greater than 0. And these two are one-sided tests. That's what we keep in our back pocket until we have to find the p-value, right? We have to find, do I need to find the area in just one of the tails or in two of the tails, right? Okay. So one of the new things that we're adding for hypothesis testing for two sample proportions is that if I'm assuming that P1 is equal to P2, right? I'm assuming that these proportions are the same. So to simplify things a little bit, by adding more stuff, I just realized, I guess, we pool these proportions. So we throw all of them into a pool cube, right? And then we just look at, okay, who's a success and out of how many, right? So we just find this pooled proportion of successes in general. Okay, so I'm going to steal the blurb from the textbook. Okay, let's see if I can make this a little bit bigger here. Whee! Love to make it bigger. There. Contained to one page here. So we use the pooled proportion when the null hypothesis is that P1 minus P2 is equal to 0. Remember, that's what I said it would always be. That's not really true. That's what it will always be for us. Okay, we could test a different value. Okay, so then we would need different techniques. Then we can't use the pooled proportion, for example, right? And so, but that's beyond this course. So for us, we will always have P1 minus P2 is equal to 0. Just are they different? In the textbook, they show you an example where it's not equal to 0. I think it's equal to 0.1 or something, which can totally happen, but for us, no. So then when the null hypothesis is that the proportions are equal, which it will be for us, use the pooled proportion, which, and I am rude and I don't even write the pooled, right? It says p hat pooled. That's a nice hint. Wouldn't that be so nice of me? but I guess I'm not that nice. Right. I just use p hat. Aha, so then the context would tell you, okay, because it's a two sample proportion situation, then it has to be the pooled proportion. Okay. Where the pooled proportion is the, and I'm gonna add the total number of successes over the total number of cases. P1 hat N1 is really just how we find X1. So if you have the number of successes in group one, then that is what it is. So this is going to be X1 plus same thing for X2 over N1 plus N2. The formula for the pooled proportion is on your formula sheet, right? And so it uses just the P hat like I have here. I'm not nice, I didn't write subscript pooled. And then how it is laid out, I should have brought it in, but it has the formula that we're gonna use, which I'm avoiding on purpose, and then where P hat is equal to this. And it has all these different ways of finding the pooled proportion. Yeah. So we use the pooled proportion to verify the success failure condition. Okay, that's new, right? What did we do for a confidence interval? For a confidence interval, we just use P1 hat, P2 hat. Right now, we're going to use the pooled proportion, still checking both sample sizes, right? And then once those conditions have been checked, then we can use the pooled proportion to estimate the standard error. So that's nice. Okay, I'm going to highlight that. If you have to check the conditions and you're not sure which ones, you would have to read the question to figure out if you're going to be doing a hypothesis test or a confidence interval, right? And if you're doing both, then you have to check all the conditions. Ugh. But you may as well just kind of get it over with. So for hypothesis testing, the conditions we check are, the first one is still independence. That hasn't changed. That's been the same for one sample proportion, confidence intervals, hypothesis testing, two sample proportions, confidence intervals, and now hypothesis testing. As soon as we have two samples, though, of course, we have to assume independence both within the groups and also between the groups. But independence within and between groups. Yeah. The second is still the success failure condition. A little bit annoying that it jumps around so much, right? The success failure condition for confidence intervals, one sample proportion as well as two sample proportions, we use the P hats that we have, right, respectively. Whereas for one sample proportion, we use the null P naught, right, to check the success failure. And now we're going to use the pooled proportion. So the pooled proportion the success failure condition uses the pooled proportion. And we need to check both sample sizes. Both sample sizes. So if I let just the generic P hat now denote the pooled proportion, then I would need to check N1 P hat has to be greater than or equal to 10. N1 Q hat has to be greater than or equal to 10. N2 P hat has to be greater than or equal to 10, and N2 Q hat has to be greater than or equal to 10. Right, where context tells me that P hat is the pooled proportion. So that's how we use the pooled proportion to verify the success failure condition. How do we use it to estimate the standard error? Okay, so now we can use P hat to estimate the standard error of P1 hat minus P2 hat. I got a little too messy for my liking. I'm pretty easy on myself with my poor writing, but that took it too far. P1 hat minus P2 hat. Remember, in general, for two sample proportions, we said, okay, we have to take into account all the information from the different samples. So technically, it should be P1 Q1 over N1 plus P2 Q2 over N2. But remember, we have the same problem that we've been facing this whole time. I don't have the population proportions, right, for either of the groups, of course. So what do we do instead? Right, instead, I use P hat, Q hat, P hat, Q hat, where P hat is the P hat pooled, if I'm being nice. With that common numerator, it might be nice to just, so we're not doing a ton of calculations, right? It might be nice to just pull those outside. So we could rewrite this as P hat Q hat times 1 over N1 plus 1 over N2. I'm pretty sure I kept both versions on the formula sheet, so just whichever one you prefer is fine. Right. Okay. The one thing I haven't mentioned is, okay, so we've talked about the null hypothesis, that's step 1. We talked about the conditions, let's call that step 0. So step 1, the hypotheses. Step 2, do the test. I haven't told you how to calculate it, and I'll save it for this example that I have. Okay, but what are we gonna do, right? In theory, we're going to see how far is my difference of proportions, so the sample difference in proportions from the hypothesized difference in proportions, taking into account the spread, right? So it's the same idea, and it is a z-score. So we are ready for an example. If it'll paste, there we go. It wasn't until this morning that I realized all the questions have to do with sleep deprivation. I don't know why all the questions, or most of the textbook questions, are about sleep deprivation and how much sleep do you get? Something going on there. The reason I chose this one to go through is because there's a ton of information here, right? And so that can be quite daunting to have to kind of pick through and figure out what it is that I actually need out of this. And there are a ton of different hypothesis testing questions that we could ask, right? And so let's just read the question. So the National Sleep Foundation conducted a survey on the sleep habits of randomly sampled transportation workers and a control sample of non-transportation workers. The results of the survey are shown below. Okay. So we have these different drivers, let's say, right? We've got the control, the pilots, the truck drivers, the train operators, and then bus, taxi, limo drivers. And then they had to report, did they get less than 6 hours of sleep, 6 to 8 hours of sleep, or more than 8 hours? We are asked to conduct a hypothesis test to evaluate if these data provide evidence of a difference between the proportions of truck drivers, okay, and non-transportation workers, which is the control group, who get less than 6 hours of sleep per day. So they would be considered sleep deprived. Okay, so out of all this information here, right, we're going to focus on the truck drivers and the control group. Okay. Of course, the question could have been about pilots and train operators, right? Who gets more than 8 hours of sleep, right? Could be a different category even. Okay. And so for us, right, we wanted to talk about the proportion of truck drivers and non-transportation workers, which means that you're essentially just going to delete all these other columns, right? These 3 columns, they're gone out of our lives forever. And who get less than 6 hours of sleep, which means we're going to be stuck on this line here. But of course, we're really only interested in these values here. And then we've got the totals. So let's jot down all the information that we've been given. And I'll develop some notation here. I'm going to let C be the control and T be the truck drivers. What we've been given is the number of successes in the control group is 35. A success in this case is being sleep deprived, but whatever. Success. The total number in the control is 292, right? So NC is 292. And then for the truck drivers, XT, let's call it, is also 35, but NT was slightly lower at 203. So from here, right, with this information, I can calculate the sample proportions. I am going to use the individual sample proportions, so I'm going to start there. And then I know I'm going to need the pooled proportion, so then I'll keep going with that. Notice how I tend to keep the order that they appear, just so I don't get, I don't know, tossed around too much here. Okay. If you don't like that, you are free to change it as long as you are consistent. So P hat for the control group is going to be 35 over 292. And P hat for the truckers is also going to be 35, but over 203. Once I do this, I'll just jot down 0.11986300137, which I'm going to round to 4 decimal places. 4 decimal places is usually good enough, unless you've got a ton of zeros, then you would have to keep all those. You're not going to round to 0. That would be weird, right? And so just kind of play it by ear, but usually 4 is good enough. 0.1199 and 35 over 203, 0.17241379331, which again, I'm going to round to 4 decimal places, 0.1724. We also need that pooled proportion. We also need the pooled proportion. Which is p hat is going to be xc plus xt, which is 35 plus 35 over the total number in that combined sample. So you throw everyone in the pool, 292 plus 203. Which is 70 over 495, which is 0.1414 repeating, which I'm going to round to 0.1414. Okay. So we use this p hat to check the conditions, which we need to do in order to be able to do the hypothesis test. So here we go. The first condition is still independence. Let's go back and see if they mentioned anything about randomly sampled. Oh, what a surprise, they did. A survey on the sleep habits of randomly sampled transportation workers. So the fact that they were randomly sampled means that I can assume independence within the groups, but also between the groups. So it checks all the boxes. And I'm just gonna use the statement that you could apply to any situation where they were randomly sampled, right? So subjects were randomly sampled, as long as it says. So we can assume independence within and between the groups. And between the groups. That doesn't make any mention of truckers or controls or anything like that. That's a generic statement that you could apply as long as it says that they were randomly sampled. The success failure condition, we use this pooled proportion, right? 0.1414. So, but we still need to check both samples. N1 times p hat is 292 times 0.1414, which is 41.288. 3/8, can't remember how many is said, which is greater than or equal to 10. Great. N1 hat is 292 times 0.8586, which is 250.7112, which is also greater than or equal to 10. So that's checked for group 1. Now I need to do the same thing for group 2. Right, you don't want to forget to do both groups. And 2 times p hat is 203 times 0.1414, which is 28.7042, which is greater than or equal to 10. And it's a little on the low side, but it will allow it. And to q hat, 203 times 8586 is q hat. Is getting sloppy here, 174.2958. which is greater than or equal to 10. Surprise, surprise, the conditions all check out. So therefore, we can assume a normal distribution. So therefore, we can assume a normal distribution with a standard error of P1 hat minus P2 hat, P hat, Q hat. I'm going to use that kind of simpler version where I extracted the numerator times 1 over n1 plus 1 over n2. Okay. We're finally ready to start this hypothesis test. So step 1, we're going to state the hypotheses. In terms of the control group and the truckers, right, we're going to have the proportion in the control group is equal to the proportion in the trucker group, right? Or if you are more proper than I am, the null hypothesis is that the difference in proportions PC minus PT is equal to 0. For the sign in the alternative, right, we wanted to evaluate if these data provide evidence of a difference, right, which is that keyword for a two-sided test, which means I have not equal to. So then the alternative is that PC is not equal to PT. Making this, right, this not equal to makes it a two-sided test. Or if you're comfortable talking about the difference explicitly, then it would be not equal to 0. There's an or here, right? You don't need to do both, just pick one that you like. Step 2, do the test. It is going to be a z-score. And like I said, what we want to know is, so it is going to be a z, spoiler alert. What we want to know is the difference between P1 hat and P2 hat, just generically. How far is it from the hypothesized difference of 0, right? Or in general, how far is it from P1 minus P2? But remember here that since the null hypothesis is P1 minus P2 is equal to 0 always, really what this would be is just P1 hat minus P2 hat minus 0. So usually we just omit it from the formula, right? We don't write minus 0. Okay. So we usually omit this from the formula. But it is important to recognize that we are still seeing how far is my difference in sample proportions from my hypothesized difference in population proportions, right? Taking into account the spread, which is the standard error still. P hat Q hat times 1 over N1 plus 1 over N2. Where this P hat is, of course, the pooled proportion. On the formula sheet that I added on the assignment, it doesn't even mention this difference here, right? So now we forget all about it. It is there, it's lurking, right? But we're seeing how far is this difference in proportions from 0? So for our question, this is going to reduce to P hat C minus P hat T divided by so many P hats. P hat Q hat times 1 over N1 plus 1 over N2 square rooted. We have all these values, and instead of scrolling back and forth, I'm going to steal them from here. 0.1199 minus 0.1724 divided by, I'm going to do the square root last because otherwise I keep having to extend it. 0.1414 times 0.8586 times 1 over 292 plus 1 over 203. Now, don't forget the square root. This morning I said I should get a tattoo that says, don't forget the square root. But then I realized that you guys need the tattoo that says, don't forget the square root. Not me. Well, yeah, I do too, actually, sometimes. Guilty, guilty. All right. Simplified, got the pre-baked version here. Negative 0.0525 divided by 0.031840750993. I wrote that out because this is, right, this is the standard error of PC minus PT hat. All right. You're not gonna need that, but in case you ever did, right, it might be nice to pause and write it out before you finish the question. So then I get a Z of negative 1.64883046. Z, we round to 2 decimal places, so I get negative 1.65. Which says that the difference of 0.0525, right, negative 0.0525 is 1.65 standard errors below 0. Right? And so now we need to find the p-value. So SEP3, find the p-value. And maybe I should put it on a fresh page. Wait. In terms of our normal distributions, Z is centered on 0, and I have a Z of negative 1.65. So this area is the one-sided p-value. If I need the two-sided p-value, which we do, we have a two-sided test, right? Then I need to find my one-sided p-value, and then I need to replicate it in the other side just by multiplying by 2. So now using the Z table, and I guess I could start down here. using the Z table, the area to the left, luckily we know how to use the Z table, right? Of Z equal to negative 1.65 is, I'm not going to go there, I'm just going to tell you it's 0.0495. Because I am running out of time here. Therefore, the one-sided p-value is 0.0495. So the two-sided p-value is 0.0495 times 2, which is 0.099. Now, the last thing, I want you to work through the conclusion on your own, but I like to throw this one in. I'm surprised I haven't busted it out earlier. If the P is low, then the null hypothesis must go, obviously. There's been so many times where I see that in the margins on a final exam. If the P is low, then the null hypothesis must go. So try the conclusion on your own, right? We have the P-value. You're ready for step 4. Try it, and then we'll wrap it up on Tuesday. All right, I'm gonna stop this recording.